Hello everyone. So in this session, we will be seeing the next topic that is feed forward network. Okay, so feed forward neural net. So feed forward neural network is the multi-layer perceptron. Okay, it's also known as the multi-layer perceptron. Okay, so which is known as MLP. Okay, for historical reasons, we are giving this coining this term. Okay, so normally consider there are inputs like x1, x2, or you can say xn 0 for that matter. Okay, and there are multiple hidden layers like h1, there is an h2, h3. Okay, and this is nothing but your hn minus 1. Okay, and this is nothing but your bias plus 1, which you can see here. Okay, so each inputs with each input, what we are giving is the weights w. You can see that these are the weights that are being applied, and we are giving it, okay, over here. So for x1 or x2, okay, we are multiplying with the weights. Even you can say that this is the xn0 also, we are applying with the weights, with the weight w. Okay, and even with the bias b, okay, has also been, okay, applied here, is also been given. So this is nothing but your bias b. Okay, let me, okay, so this is my bias b. Okay, and this is my first input layer, and this is my hidden layer. Okay, and from the hidden layer we are having the output layers like y1, okay, y2, and like that we have yn minus 2. So we are giving the inputs, okay, to different. So this from the hidden layer, it goes to the output y1, y2, and yn minus 2. Okay, so this is the output layer. So let's go with the binomial logistic regression. Okay, so for binomial logistic regression. So binomial or binomial, okay, logistic regression. You have this input x1. This is nothing but my I. Okay, so ith input like that up till xn. So we have input from x1 to xn. So when input is applied with the weight w, okay, so this w is the weight, which is nothing but a vector. Okay, for a binomial logistic regression, this is nothing but my vector, and this is nothing but the input layer, which is nothing but x1 up to xn. So this input is nothing but is in also in the vector here. So input is also a vector, okay, and the weights are also in vectors. So you can say that this is nothing but my w1. Okay, this is like that, multiple inputs are there. Okay, and this is nothing but my wn. Okay, and along with that there is again plus one, which is nothing but the bias. Okay, so bias is nothing but b, and this bias is actually a scalar. You can see that the weights are nothing but in vector, whereas the bias is in scalar. So this is my layer 0. So in neural network, you don't consider the input as first layer. Only the that the output layer is considered the layer, or the hidden layers are considered as first layer. And you can see that when I'm applying this, the input with the weights is applied to this node. Here we are using the sigma function. So why the output of this is nothing but the activation, what we're getting is sigma of w into x plus b. Okay, this is for the layer 1. And this y, what you can see here is nothing but your y is nothing but your scalar. Y is nothing but your scalar. So this is my layer 1. So this y is nothing but scalar, and this is nothing but my output layer. So output layer, for the output layer, what is being applied is the sigma. This is nothing but sigma node. Okay. So in binary logistic regression, okay, it can be considered as a one layer network. Okay, so because it is a binary, okay, so only one layer. But when it comes to the multinomial, so it was a binomial. So in multinomial, okay, logistic regression. So sorry, a multinomial in multinomial logistic regression, as a one layer, okay, network. So if you're considering the fully connected single layer network here, so again here I'm taking x1 as the input. Okay, like that there are xn inputs for that matter, and this is my bias plus 1. So when I'm saying a multinomial, not a binomial, a multinomial means you will be having the multiple outputs here. S, this also has S, this also has S. So you'll be getting a multiple output. So this is nothing but my y1. Okay, so you can see this is yi or something, and this is nothing but yn. So here you can say that the weights, okay, that is nothing but my w. This is the weights that are being applied. Okay, so weights are being applied. So from this, from every node, you can see the weights are being applied over here. Same thing here, from here also the weights are being applied. Sorry if my figure is not neat, but the basic core idea is what you should understand. Okay, and this is nothing but the bias, okay, which you are getting, which you are applying. Okay, that is this is nothing but b. Now here in the multinomial, as you can see in the previous case, your w was a vector, but here it is w is a matrix. Okay, and your b which is a scalar will become a b will become a, so b is a vector. Okay, and your y, which is nothing but output, where I was applying the sigma function, iteration function, but since it is a multinomial, so I'm applying the softmax. Okay, so softmax of wx plus b, where y is nothing but your vector. So in the previous case, it was the y was a scalar. Here y is nothing but vector. Whereas your input layer is nothing but your scalar. Okay, scalar. So let's put a reminder that for you, softmax. So I had already made a video on softmax, so you can also go through that. But a softmax is a generalization of sigmoid. Okay, so for a vector of vector z, so vector z, okay, of a dimension k, okay, dimensionality k, the softmax is the equation for softmax. Yes. So softmax of z is nothing but equal to, okay, exponential, okay, z1 divided by summation of I is equal to 1 to k exponential, okay, z of I. Same thing, exponential z of 2, okay, divided by summation of I is equal to 1 to k exponential z of I. Same way, exponential z of 3 is summation I is equal to 1 to k exponential z of I. So what you can see here is this softmax for ith in, so instead of writing this, for I can say that for ith z of I, so you can write it as exponential zi. So because z1, z2, z3 up till, you can say that is zk, you can say. So one, uh, so this is here 1 up till I is up till 1 to k, okay, divided by summation of j is equal to 1 to k exponential z of j. Okay. Because um, that many times you can say that it is repeated. Okay, so for 1 till k, okay, this exponent of j has been written. Okay, now you're, if applying the example of, for example, if your z value, so I'm telling about your z is the vectors, okay, z is the output. So for z, if it is equal to 0.6 or 1.1 or minus 1.5 or 1.2 or 3.2 or minus 1.1 values are there. The same thing if you are applying the softmax activation of z. So you'll be, if you calculate and see with that formula, which I had, equation which I had given is 0.055, 0.090, 0.006, okay, 0.099, okay, 0.74 and 0.010, okay, is what you'll be getting. So this is about the multi-layer notation. Now if you are taking yes, okay, second, now if you are taking, let me check, I think there is some, okay, okay, let me take the another uh, window for that matter. Okay, so another PPT. So now let's see the two layer neural network with scalar out. So in this case, um, you have we are taking, because in the previous case we had seen that it's a single layer. So this is about it's two layers. Two layers means this is nothing but your x1. Okay, so this is nothing but your ith input. So like that, you have x n, and this nothing but your bias. Okay, so this is the input is given to the hidden layers. So these are the hidden layers. So This is what you can see here. Okay. And so you are applying the bias plus one. Okay. So bias is also given to the hidden layer. Okay. So this is my B. Okay. And this is nothing but my W. So you can see that this is my input layer. Okay. Input layer is a, so this input layer is generally a vector, and the hidden, this is nothing but hidden unit. So the hidden unit is considered as first layer. This is considered as zeroth layer. Okay. And this is nothing but I am applying the sigma activation. So it's a sigma nodes. All these are nothing but sigma nodes. And or the output is this, my output. Okay. So you can say single output in for that matter, you can say. So here you can say that this is nothing but the output layer. Okay. Output layer, you can say this is nothing but sigma node. Okay. So here you can say that this the you can say the second layer. Now the output function y, this my output function y is nothing but the sigma applied to the z. So this is my um, to the z output whatever I get here. Okay, I am applying the sigma function. So here you can say that whatever the sigma function that is applied to z. Okay, what is z here? Z is nothing but the weight. This is my weight, which is nothing but u. Okay, and the this is that's what u into h. H is nothing but the previous hidden list. So this is my h, where h is nothing but again this was also a sigma. Okay, w x plus b. Okay, so this is my w. Okay, applied to each x input. So w is applied to x1, w is x for this xi. Okay, xi plus 1, then xn. So that's all, plus the bias, that is nothing but this plus 1 is nothing bias, so which is nothing but b. So this the wx plus b is applied. Okay, and what you get is the output of this is uh, applied to the so we are applying the sigma function to the wx plus b, and what you get is nothing but the h as the output. This h output, okay, is acting as an input. Okay, in the next layer. So this u is nothing but the another weights, another set of, just like how your w is the weights for this first layer, u will be acting as a weights for the second layer. So z is equal to 0 into h, this number another weight into the output what you get here. Okay, now this z output, okay, again this is nothing but to your z, just like how these are h layer, this is nothing but z. Now to this z, okay, I'm applying the activation, which activation, that's but sigma activation function. So then what you get is nothing but the y. So I get here y. Okay, so this is about this is for the single. So here y is nothing but a scalar output what you get. Okay, because only one output, only one node output, what is it? And the activation can in this what I'm applying is sigmoid. But in the previous case, I it's not necessary that I have to keep sigma. I can also keep ReLU function, okay, or tan h function as the activation. So not necessary that in the for the hidden layer you have to use sigma function. You can also use ReLU or tan h also. Okay. Now, if there are more than two output layers, okay, if there are more than two output layers, like you can see that your this is my x1. Again, you can see that this is my xn, and this is nothing but the bias plus one, and these are nothing but my hidden layers. Okay, Now I am applying the, okay. Now this is the bias which you can see here, okay, which is nothing but B. Okay, this is my B, okay, and this is nothing but my W. This is my input layer. So this input layer is nothing but a vector, okay. Your W is weight which is being applied, and this is nothing but my H, hidden layer. So hidden nodes, for the hidden nodes, okay, I am applying the sigma function. Sigma functions are being applied, okay. So here H is equal to sigma of Wx plus B. So what is W? This nothing but weight, and the X, and this nothing but B, and to this sigma activation function. So what you get is the output is nothing but H is equal to. So this is the output. For the output, we are applying the sigma activation function, and not that's what I was doing even previous case. So this need not be sigma. We can also use rel or tan H in this case, and this H here, okay, is nothing but your W, which you can say in the previous case, which was the weight, and H is nothing but the output that you are getting. Now to this, what I am applying is the this is the output which you get. Okay. Now here H is not a scalar; it is a vector. W is nothing but a matrix. Okay. B is also not a scalar in previous, so this also becomes a vector in this case. So and this input layer is also a vector. Now, so this was already explained in the previous slide. Now again, you can say that here instead of sigma function, so this is all my output layer. Okay, I am using the sigma node, but there are, since there are multiple node outputs, so I am using a softmax. Okay, softmax activation. So where Z is nothing but equal to, okay, so this is my weight U, just like in previous case. So U into H, where Y is nothing but a vector. Okay, Y is nothing but a vector. Output is nothing but vector. Same way here, H is nothing but a vector only. In the previous case, your Y was a scalar. Now in this case, it is a vector. Okay. So here also H is also a vector only, not a scalar. Okay. Even in previous case also H was a vector only. In this case also H is also a vector, and Y is nothing but a scalar. Okay. Now, so this is uh, uh, for the two layers. Okay. Now, for the notation, for the multi-layer notation. Okay. For the multi-layer notation. So consider this is my X1, this is my I, this is the other node and the Xn. So these are multiple inputs. Input is a plus one. This is nothing but my, okay, the hidden layer J and like this. Okay. And these are nothing but my weights that are applied. So this is my W of one. Okay. So for weight that is in the first hidden layer. Okay. Okay. So this is the connections, and the for biases, you can see these are the, this is the bias P1. Okay. So this is my bias B of one. Okay. And to this I am actually this is my output. So for this we are applying the weight W of 2. Okay, and this my again you can say that output what you're getting from here. Okay, so this is the output, and for this I'm applying the bias B of 2. Okay. Now what the equation what we get for this is, okay, so the equation can be written as, okay, for the output y is equal to a of 2. That is nothing but the this is the a of 2 is nothing but the output of, okay, the w and the output from the hidden units, weight and the output from the hidden units. So that is a of 2. So a of 2 is nothing but equal to the, that is what, the sigmoid function that is applied to the previous z of 2, whereas z of 2 is nothing but the output from the, that is coming from the hidden units. Z of 2 is nothing but w of 2, okay, into a of 1 plus b of 2. Okay, so the weight that is applied to the previous output that you are getting, plus the biases, the current biases, that is nothing but a z of 2. Whereas you can say that mm, this a of 1 is nothing but the activation function that is applied to the previous output, that is nothing but z of 1. Okay, and this z of 1 is nothing but equal to w of 1, okay, a of 0, which is nothing but the previous activation, so plus b of 1. Now the activation function that applied for this can be also be a ReLU, and for this, okay, normally the preferred is nothing but the sigmoid, okay, for a single node output node, or softmax is applied for multiple nodes. Okay, so this a of 0 is nothing but the previous output. So since it is a input, that is a of 0 is nothing but the input that is being given over here. Okay, so this is the input that is being given. Okay, so from a of 0, okay, you are applying that to you are applying weights to it, okay, along with the bias, okay, b1, and what you are getting generated is nothing but the z1. Okay, that's what we has written it over here. Okay, next is the proper way the equations can be written. So you can say that if this is my node, okay, so what we are applying is the summation of the multiple inputs, that is applying the x1, okay, adding x1, x2, x3. So these are the different inputs, x1, x2, and x3. And to this, we are applying weights W1, W2, and W3 are the multiple weights that are being applied. And this is nothing but the biases, B. So bias can be +1, okay, which we are doing. Now to this bias, okay, the a bias is added to this input, different inputs with weights. Okay, we are doing performing summation, and what we get is nothing but a sigmoid. We are applying the sigmoid function to the output. So the what we get is nothing but z. So after summation, what we get is z. So what we are performing? We are performing the sigmoid function to this z. Okay, and what we get is nothing but your, okay, a. Okay, so this uh, a is nothing but your output y. Okay, now the for two layers, so it is written as z of 1 is nothing but equal to w1 a of 0. So this is for first layer, okay, and for the second layer is nothing but AF1 is nothing but equal to the activation layer, activation function that is applied to the first layer. Okay, so the output from the first layer, we are applying the activation, any sigmoid or Rayleigh or tan H. Okay, then what we get is the out. Then we are performing the output for the second layer, so which is nothing but the W2 into AF1, that is this particular output, plus BF2, that is nothing but the bias that is applied in the for the after the for the output layer. Okay, so AF2 is nothing but equal to this is the bias in the second layer which we are applying. Okay, uh, into Z of 2. So bias which is applied to the second output layer, that is this output layer. Okay, and after applying the not bias, sorry, the activation function that is applied to the output layer, activation function that is applied to the second layer. Okay, and for that what you get is the A2. So which is nothing but y hat is equal to A of 2. Okay, so this particular aspect, okay, I have explained in this particular equation. So programmatically, so if you're writing a C program for this, so fire I in 1 to n, so Z of I is nothing but equal to W of I, okay, into A of I minus 1 plus B of I, and your A of I is nothing but the activation function G of I that is applied to the output Z of I. Okay, and your Y hat is nothing but A of n. Okay, uh, so this is your explanation for your, okay, the feed forward network. So if there is any queries, okay, you can ask. Thank you so much.